evening. Do you know what a robotic telescope is? Well, it's a telescope that, once brought into action, can operate entirely on its own. The astronomer who brings it to life needn't be near at hand. He needn't even be in the same continent. Therefore, they can be put in all kinds of places, and they have very special uses. They were pioneered largely by the Liverpool John Moores University, and the first one, the Liverpool telescope, was on the island of La Palma. There are now two more, Forks North and Forks South, and together they make up what's called a RoboNet. With me now, I'm delighted to say we have Professor Mike Bode, who looks after the Liverpool telescope, and Dr. Paul Roche of the Forks telescope. Welcome to the Sky at Night. First of all, may I come to you, Mike? Why RoboNet?
Well, first of all, a single robotic telescope is important because it can observe things in a very flexible way. It can react very rapidly to things that change in the sky, things that are unpredictable, and it can also observe things systematically for very long periods of time as well. So conventional telescopes generally can't do these things. Now that's for a single telescope on a single site. RoboNet is important because it's a distributed network of telescopes around the globe. So we have telescopes in the northern hemisphere and the southern hemisphere, and we have them at different longitudes. So we can effectively observe anything, anywhere on the sky, at any time of the day, and we can continue to observe it for as long as is scientifically important to do. Because what we can do is pass the observations from one telescope to another round the globe as it becomes dark in one place and it's still light in another.
We have so far the Liverpool telescope and the two Forks telescopes. Where are they?
Well, Forks Telescope North is at the Haleakala Observatory, which is on the island of Maui in the Hawaiian Islands. And Forks Telescope South, which began operations just a few months ago, is at Siding Spring Observatory in Australia. And with the Liverpool telescope on La Palma, they form the beginnings of this RoboNet network. Now, these are 2-meter class telescopes, so they're not the biggest telescopes in the world, but they're sort of optimal for the sort of science that we want to do with a network like RoboNet. They can be controlled in this robotic mode and operate round the clock, but what we do with the Forks telescopes as well is we allow them to be controlled live by observers from the UK, and they actually take control of the telescope for half an hour at a time.
With no operator there, how does RoboNet work?
Well, each telescope has some very sophisticated software, which is called the robotic control system, which really replaces the human observer. So each telescope is, for example, linked to a weather station, so it knows whether it should open up, whether it can observe. It has a list of potential objects that have been fed into it from the selection of programs that it could undertake, and the software automatically selects which object is the best one to do next. So during the course of a night, there is no human intervention on any of these telescopes. Now on top of that, we have software which has been developed which actually picks which telescope in this global network is the one to use for this particular observation now.
People are going to ask, do you really need astronomy?
Well, we're sometimes accused of taking the fun out of actually going to these big observatories and using telescopes, and it is a serious point that we still want astronomers to be very familiar with how equipment works and what the problems can be and how much to believe your data. But on the other hand, you really do need the human brain to actually analyse the data that you get back and to therefore understand what's going on.
These things operate entirely on their own, but they've got to be maintained, so there must be somebody there.
Well, we certainly have people on Hawaii and in Australia that go along and sort of give the thing a kickstart every now and then. But I mean, they're pretty reliable. The way they've been built and designed is so that they don't really require very much human intervention. But inevitably, there are a few little things that need to be topped up or reconnected or just given a good boot every now and then.
Paul, if you want to use this telescope, how do you go about it?
We run the telescopes entirely through an internet website, so a user will log on, they'll have a username and a password, typically their school name and a password their teacher's decided on. And at that point you can either select a book time. If you already have a session booked, you sit there and wait until your session starts. And our observation sessions start on the hour and the half hour, so a school is sat there with their teacher hopefully waiting for their session to begin. And then when that magic time begins, they have 30 minutes at that point to control the telescope. And it's entirely up to them what they do with it. We have no ability really to stop them doing what they want.
What kind of things are they doing?
Most of what we're doing at the moment, I guess, is fairly localized. So it's near-Earth objects, things that move relatively quickly so that they can actually, within a 30-minute session, children nowadays have a fairly low attention span in some cases. So we like to try and do things that they can see things happening, things changing.
Such as?
Well, near-Earth objects are quite nice because in the space of about 15 minutes, a near-Earth object will actually cross the field of view of the telescope. So they can make a little movie and show the asteroid moving. We've got a lot of interest in things that are changing in brightness. For example, variable stars, supernovae are particularly interesting to children as well, because that's something they have to learn about in the curriculum.
And what about Liverpool telescope? Same kind of thing?
Yeah, well, our schools program on the Liverpool telescope is done in an offline mode, so that schools actually propose objects to observe. Those go into the professional queue, and then if the weather's good and everything else is right, then the observations are done overnight, and the next day the schools get the observations back. But primarily the Liverpool telescope is focused on science, and its science programs range from the sort of thing Paul was talking about in our local bit of the universe in the solar system to cosmology projects in the distant universe.
You mentioned gamma ray flares. Can you say a bit more about those?
Well, gamma ray bursts were discovered by American spy satellites in the late 1960s.
What are they?
Well, in the late 1960s, obviously these gamma ray satellites were military satellites. They were looking for violations of the test ban treaties in space. And what they found were gamma rays not coming from nuclear explosions, but coming from natural phenomena. They remained secret until 1973. And between 1973 and 1997, I think it's fair to say that there were almost as many theories as there were gamma ray bursts observed, and we really didn't have much of a clue as to what they were. And the real breakthrough was when a satellite called Beppo-Sachs managed to pinpoint where one of these gamma ray bursts was, and the telescopes on La Palma, the Isaac Newton telescope and the William Herschel telescope, followed this up the following day and found what's called an optical transient, and were able to locate that. And from there on, we were able to determine that gamma ray bursts were actually associated with distant galaxies, and therefore were cosmological objects. We then got a handle on the energetics, which turned out to be absolutely enormous, in some senses unbelievable. And it turns out now that of the two classes of gamma ray bursts that we know about, the long bursts and the short bursts, long in this sense lasting tens of seconds very typically, so not very long, the long bursts, we're now fairly confident that they are related to objects called hypernovae. So these are stars of 30 or 40 times the mass of the Sun or more that come to the end of their lives. They've burnt everything up to iron. When they get to iron, the core collapses, everything collapses, and then there's an enormous bang. We have a black hole left in the middle, and debris going out, shock waves going out at near the speed of light into the interstellar medium. And we see a flash of gamma rays, then followed up by optical emission, which is what gives rise to this optical transient. The optical transient lasts much longer than the gamma ray flash, and that gives us the time, albeit maybe just minutes to an hour or so, to actually go and observe them from the ground.
Because there's no way in which you can predict them.
No, that's absolutely right, and we rely on the fact that these spacecraft now, like Swift, are detecting these gamma ray bursts, localizing them very quickly, and then sending the results to telescopes on the ground, such as the Liverpool telescope and the Fawkes telescope.
How frequent are they?
Well, we're seeing several a week. I mean, it all depends on the thresholds of the satellites that are actually looking for them. But as Mike said, we see a lot more of them now. In the past, the problem's always been that we couldn't localize them on the sky. So you'd be basically told it's somewhere in the constellation of Hercules.
Yes,
now we can get positions very, very fast and very, very accurately, which means we can point optical telescopes at them very quickly, which is where things like RoboNet are ideal, because we can slew the telescope very, very rapidly, and within tens of seconds or minutes be on sky taking images and looking for these optical transients.
You have to remember that the Fawkes telescopes and the Liverpool telescopes are the largest robotic telescopes in the world, and therefore are the largest telescopes getting on so quickly to these gamma ray bursts. And what we've been able to do in several instances is follow the evolution of the light from these objects over several days by passing the observations from the Liverpool telescope to the Fawkes telescopes and then back again as the Earth revolves and day and night go round past the telescopes. So this has been a great success and a real demonstration of what a global network of telescopes can do.
The only disappointment for us, I guess, is if a school is using the telescope at the time, they get overridden by this gamma ray burst. But we try to explain to them that we don't actually control these events at the edge of the universe. It's not our fault.
We have satellites. What about Swift, for example?
Well, Swift has caused a revolution a further evolution, I guess, in our understanding of gamma ray bursts. It's a joint US, UK, Italian satellite that was launched towards the end of 2004 and is discovering and localizing gamma ray bursts at the rate of a few a week. And for each of those, it's beaming the positions down to the Earth for telescopes such as the Liverpool Telescope and the Fawkes telescopes to react to. And what it has is a wide-angle gamma ray detector. It's looking at a large chunk of the sky. This is a detector called the BAT, and this immediately localizes to a certain extent where the gamma ray burst has come from, and then they swing the telescope to observe that region with an X-ray telescope called the XRT, which is built at the University of Leicester. And the XRT then further localizes the event to the point at which ground-based telescopes like our big robots can actually point and be fairly certain that the gamma ray burst is going to be in their field of view.
All these three work together?
Absolutely. I mean, the Fawkes telescopes are operating in this sort of joint education and research mode, but as part of RoboNet, then it's entirely research-based with Liverpool.
Yeah.
Are you planning more telescopes?
Well, Las Cumbres Observatory, the organisation which now effectively runs the Fawkes telescopes, is planning many more telescopes. There's an eventual plan to have something like 50 or 60 telescopes, smaller apertures, 1 metre and ½ metre telescopes, but on exactly the same model that RoboNet runs, with telescopes distributed around the globe, northern and southern hemisphere, and different longitudes.
The other area that RoboNet has particularly been concentrating on is gravitational microlensing, looking for exoplanets. And this is a technique that relies on the fact that light is bent by a massive object. So if you imagine a distant star, and then across that line of sight moves another star, and the light of the distant star is bent around it. And that actually causes a magnification effect, so that you see the star brightening and then fading away again over a period of something like typically a month. And many of these gravitational microlensing events have been seen. Now, if you have a planet going around this intervening star, then you get another little blip due to the gravitational field of the planet. That blip lasts a very short period of time, although the magnification can be quite high. So it lasts, say, a day. Now, it's a little blip on the light curve, the main light curve. And what we're looking at with RoboNet is finding that little deviation and then automatically concentrating on it and peppering it with points. And out of the 4 planets that have been discovered by this microlensing technique so far, 3 of them have involved RoboNet observations, and 1 of them is the most Earth-like planet in some senses discovered to date, with a mass of only something like 5 times the mass of the Earth. So now we're really homing in on this technique, and we're closing the loop to make all this automated. And we have high hopes that this season, particularly using Fawkes South, we will add more exoplanets, perhaps of even lower mass, continuing to approach that magic Earth mass.
Mike, Paul, thank you. Do stay with us. Now, there are plans to expand this robotic network in more countries and with more telescopes. And behind the scheme is millionaire Wayne Rosing. He formed the Las Cumbres Observatory, and when Chris was in California, he found out about it.
Santa Barbara in California won't feature on too many lists of the world's best observing sites, but astronomers here will soon be able to coordinate observations from a global network of telescopes. The town is more famous for its sand and surf, but the moisture in the air gets in the way of the clearest views, but not for astronomers who do their observing via the internet. Still living out of boxes in this new location, astronomers here are helping to make a vision come true. A global education and research project allowing schools free access to some of the most modern telescopes on Earth. The man with that vision is Wayne Rosing, who made his millions by being the business brain behind one of the largest internet companies. His first love was astronomy, which is what he's now returned to in what passes for retirement. The Las Cumbres Observatory is now responsible for the two Folks telescopes and the school's projects they support. The plan is eventually to extend the school's project worldwide with more telescopes at different sites, all operated remotely and between them working 24 hours a day, 7 days a week. In the warehouse, his team are assembling telescope mounts and testing technology. It's early stages yet, but Wayne already has plenty of gadgets to play with.
This is our test telescope. It's going at the Sedgwick Nature Preserve out in the Santa Ynez Valley. It's about 45 minutes from here. It will be part of our network, and it will be used by university students and school kids, actually grade school kids all over the Santa Barbara County area.
And it'll be operated remotely?
It'll be operable either remotely, robotically, from anywhere in the world, or you can go in the observatory and use it traditionally.
Education is central to the vision of the Las Cumbres Observatory. The Folks project for schools already has over 10,000 students, and Wayne Rosing wants that number to grow.
There are two things we're trying to do. The first is education. And what we'd like to do is set an example internationally of really inquiry-based science experiences for children, and to help teachers learn how to teach instead of transmitting information, but create an environment where kids inquire and develop their own power of how to learn, and to learn in a way that's consistent with scientific sort of approaches to things.
To actually do science instead of hear about it.
And to learn by inquiry. So that's one objective. The second objective is to have a scientific mission, which is to look at these long time series observations and to have telescopes all over the world available to look at these transient phenomena, these rare things that come out of these survey telescopes. And someone has to be there to look at them. They happen fast, they happen short, they're very bright, and it means it's high energy, and it could be new physics. And so that's an important area we think we can make a contribution to. And I'm personally interested in seeing if there's some science there that's going to be exciting.
During the next 4 years, 50 telescopes will pass through this workshop, be assembled, and then be shipped out to observatories around the world, from Mexico to Pakistan and Chile to South Africa. His experience running a dot-com business taught Wayne that the development of the information superhighway is essential if his global vision is to become a reality.
One of the unfortunate things is there's many places in the world where the internet does not exist, or it only exists in a very few places. But I think the power of what we're doing, if it's successful, will lead other governments in some of these countries to understand that by bringing the internet to their schools, it democratizes all the world's information when you can access it.
And that's exactly what you're doing with observing. Suddenly, a school kid can be competing for time with somebody sitting in a posh university.
That's absolutely right.
Joining the two Folks telescopes will be a fleet of smaller telescopes distributed amongst the 7 sites ringed around the globe. It's an impressive plan. Free access for school children and researchers alike. For the Las Cumbres Observatory, the skies will forever be dark, allowing access to the night sky no matter what time it is in the classroom.
So there's plenty going on. Welcome back now, Mike and Paul. Paul, you're talking about school children science. What kind of science are they doing?
Well, most of the schools start off with something simple like colour imaging. So they're taking images of galaxies and clusters and individual stars even. And once they've done that a few times, I think what they'd like to do is to progress onto something a little bit more scientific, say with a bit of physics and a bit of maths in there as well. So, for example, we've had children measuring the rotation of asteroids, near-Earth objects and asteroids in our solar system. Beyond that, then, we're looking at variable star research, so children actually observing occultations and cataclysmic variables and stars which are varying in brightness. Supernovae are another very popular area, and it's actually part of the curriculum that children have to learn about the life cycle of a star.
Well, it's night time in Hawaii. Sky's clear, no time like the present, so let's go online and turn straight over to the Folks telescope. Remember, we are actually going to control the telescope 10,000 miles away from my study in Chelsea. So over to Hawaii.
And the weather's a little bit better there than it is here, so let's hope that it stays that way. Well, what we're going to do first of all is select the object we want to look at. So I thought, given the time of year and the time of night that it is in Hawaii, M27 is
a good one,
very
yes.
nice object to try, and it fits perfectly into our field of view. So if you know the name of the object, you can just key it in here and hit search, and it will tell us whether the object's visible. And that little green tick is what we're looking for.
It's a planetary nebula.
Absolutely, and it's just about the right size to get a nice image. So we literally click on that. It shows us roughly where the object is going to be in the sky,
Yes.
whether there's any bright stars nearby. There's nothing that's going to cause us problems with overexposure. So we click Move Now. We normally have a little webcam image here showing you the telescope moving live, because the kids like to see something that's immediate feedback for them. But the telescope is now slewing, we have to assume. We've got a message telling us we're pointing at the right object, so now we're in the right part of the sky.
Yes.
The next thing is just to select the filters we're going to use to observe.
Yes.
So maybe just to make sure that we're looking at the right area, let's just take a visible image first of all.
Yes.
Just in single filter. So we'll take 60-second exposure time, and we'll take a single image. We won't try and do anything fancy like a mosaic. And the hope is that once they've taken their images, they will then follow this up in the classroom by color processing the images and making posters and articles for their school newsletters. We've had schools making calendars and things using their own images.
Yes,
So take 12 images and make a nice annual calendar, which they can then sell through their PTA. Okay, so it's now telling us the observation has been completed. Click OK, and we should get a black and white image, which should bear a resemblance to M27.
And we have. It's a lovely picture too.
There you go. Now, if we wanted to make a colour image of this, we would just simply go back and re-expose the object with new filters. But I think let's be a little bit adventurous and try and find something else.
Remember, this is actually live, all the way from Hawaii.
So the next object we want to look at is a galaxy this time, a spiral galaxy called NGC 7479. This is probably not one of those familiar objects that a lot of people will look at, because one of our problems is having a large aperture. We need to look at objects which are suitable for the size of the mirror that we have. We can't look at Orion or a constellation. We can look at individual objects really, but in great depth. Okay, so our colour image is now finished. So if we click on the button here, we should now get a colour image of this galaxy. And this is just a quick processed image, and obviously galaxies are fairly grey and white when we look at them like this, but we can process that image if we want to later, and we could bring out some of the detail. You can already see some of the dust lanes and those beautiful spiral arms there, but if we process the object even more, I'm sure we could get a fantastic image from that.
Well, controlling that telescope has been fascinating. Well, where does the Liverpool telescope fit in with all this?
As well as the core programs that I mentioned that we've already been undertaking with RoboNet, we'll now be diversifying into other parts of astronomy, including observations of supernovae, and in my own field we'll be looking at novae in our own galaxy and external galaxies to try to understand more about their explosions, and in fact for novae in external galaxies, how to use them more accurately as distance indicators in the wider universe.
And of course, you're training the astronomers of the future.
Indeed, indeed.
Mike, Paul, thank you very much.
Thank you.
Thank you.
And now our news notes. A major dust storm on Mars. And here's a picture of it by Damien Peach. These storms do occur. They can be planet-wide. There haven't been a major one like this for a long time now, and fascinating, but this is not terribly good news for the rovers, is it?
No, the rovers, Spirit and Opportunity, depend on solar power. So when the atmosphere gets murky, as it does during a dust storm, the amount of power they have available drops right down. And right now they're only just getting enough to keep themselves alive. Opportunity had been due to take the plunge into Victoria Crater, this crater it spent the last year or so exploring, but now it's just sitting on the rim, and we're hoping that both of them will hang on for the rest of the dust storm and then be able to continue exploring afterwards.
I've seen several of these dust storms. They usually last for 3 or 4 weeks.
So we're about halfway through. We should be okay, but let's hope the rovers survive.
Let's hope so. Now further out, Saturn. That strange satellite, Iapetus. Smaller than our moon, with a weird equatorial ridge. And a theory now about that. How did it form?
Yes, well, the ridge shouldn't be there. It's too big to form on a small moon like Iapetus. So here's the long story of what we think happened. Iapetus used to rotate much more quickly than it does today, spinning round about once every 5 hours. That meant that it's not a perfect sphere, it's an oblate spheroid, like a squashed sphere, a bit like Jupiter is today.
Or a squash balloon.
Exactly. But then friction caused Iapetus to slow down. Then it tried to go back to being a sphere, but the crust was solid, and so it buckled around the centre, and that's what produced this ridge that we see today.
Unlike anything else in the solar system, as far as we know. And of course, a new small moon there, Frank.
Yes, well, temporary name Frank,
Yes.
discovered by Carl Murray at Queen Mary and his team. And this is the 60th moon of Saturn, so whole host of things orbiting the ringed planet.
This one about 1.5 miles across.
Yes, completely insignificant, but rather fun.
Now, much further out still, Pluto. No longer a planet, now a dwarf planet, with a satellite which I'm going to call Charon. And it now seems from deposits on the surface that there are ice volcanoes there too.
Well, we haven't seen the volcanoes themselves, but astronomers using the Gemini North telescope have seen the signature of water ice on the surface of the moon.
And hydrates too.
That's right, and what's more is they can tell these have a regular structure, which means they're recent, probably formed in the last 10,000 years. So the conclusion is, just like we've seen recently on Saturn's moon Enceladus, that these are the deposits from icy volcanoes, even all the way out near Pluto.
Even underground water.
Possibly. I mean, it's a long step to get to underground ocean.
Let's not forget the Perseid meteors, always a reliable shower, and this year it'll be good. The moon's out of the way. The actual maximum is 2 o'clock in the morning of August the 13th.
That's right, that's the peak where you might expect up to maybe 80 meteors an hour. But go out any night, preferably just after midnight, for a week either side of that date, and you should see some bright, spectacular meteors, all of which will, of course, appear to come from the constellation of Perseus. But don't look at Perseus, look maybe 40 or 50 degrees away from that, and you should see some nice long trails.
So, plenty in the solar system. Now, out beyond the Kuiper Belt, and that's your territory, Chris.
Yes, and let's start, as we seem to do every month, with extrasolar planets. For the first time, water has been directly detected in the atmosphere of one of these hot Jupiters, a giant planet close to its parent star.
Which we haven't actually seen it.
No, we haven't seen the planet, but we've now got a spectrum of its atmosphere produced by a cunning technique that subtracts the light from the star. And for the first time, we've seen the water that we expected to be there. So it's confirmation that our models of these things are pretty good now. We're predicting their atmospheric composition.
But of course, galaxies. They come in many types. There are spirals, like our own, ellipticals, irregulars, galaxies merging, all kinds of galaxies. And there are so many now, they've not all been analysed yet. And now you've started a new program, because I'm involved in too, so in a very minor way, to classify these things.
Yes, this is a project I'm involved in Oxford with astronomers from Portsmouth and Johns Hopkins University to try and classify 1 million galaxies. And what we want people to do is sort them out by shape. So there are 2 main types of galaxy. There are the spiral galaxy, like the Milky Way, and then there are these big balls of stars called elliptical galaxies. And looking at those two, they're fairly easy to tell apart. But the human brain is much better at doing that than a computer is. So the only thing to do is to look at images of these galaxies and sort them out. We have 1 million images from the Sloan Digital Sky Survey, and if you log on to the website, which is galaxyzoo.org, you can go and look at these images, and many of them haven't been seen before. Let's start here. This is just a random galaxy from the sample. What do you reckon to that one?
Oh, that's an ordinary spiral.
So all we do is go back to the website and classify that, and then it presents you with the next one. I have to warn you, this is addictive, because you never quite know what you're going to get
I
next.
know. You've done 10, you want to go and do 20.
Exactly.
You spend an hour before you realise it.
Yes.
I know.
And thanks to the efforts of, well, so far more than 70,000 people all around the world, we're well on our way to having a good classification for all 1 million galaxies.
So as well as being fun, this is really valuable science. And the point is, everybody can help. So if we help, others will join in. Chris, thank you very much.
Pleasure.
Next month, a little black magic with the Astronomer Royal for Scotland. Till then, good night.